Swayam Prabha. Digital India. Educated India.
Get started with the fundamental aspect of thermodynamics. That's the second law, and second law is something that is a law that is applicable to all scientific disciplines as just as the first law. So let us see how to understand the second law purely from our human experience. As you might know that we have discussed several experiments here, and these experiments are some experiments where we cannot really prove the first law or the second law. That is not the goal of this, but it is just to record the human experience, and this experience is such that you derive some certain conclusion out of it in a very general form, and you will see there is no exception to it. So that is the thing that we must remember. It is not a law that immediately can be proved by an example, because examples are not proof. So by example you can illustrate the actual law, but it is not a proof. So let us to re-examine the to understand the second law, we try to re-examine some of the experiments that we have already discussed. So one such experiment was a Joule's experiment. So Joule's experiment is a very fundamental experiment that establishes a relation between the heat and work. So let us come back to that experiment. So re-examination of some experiments in the context of first law that we discussed. So one such experiment is the Joule's experiment. I am not going to elaborate the diagram, but sketchily try to make the point as follows, that we have considered a system in an adiabatic enclosure. The scheme is like this. This is an adiabatic enclosure in which I have a system, I have some water in the system, and there was a paddle that is being rotated by a wheel, and there is a mass. So there is a falling mass. The falling mass is attached to the string, and this string actually pulls this wheel, and the wheel rotates, and that makes an agitation inside the system, and that raises the temperature of the bath. So we have a system here. System is basically water, and this is the surrounding. In surrounding, I have a mass which is a falling mass, and falling mass, and the mass m and the height is h, so mgh was the work done. So what you do, you allow the mass to fall, and there is a free fall, and there is a rotation in the wheel, and the temperature is increased. So that was the conclusion. The temperature is increased, and there is a fall in the surrounding, or there is the weight falls. So if I write, so that observation is this. So observation, I write it again. Temperature rises in the system. Mass or weight falls in the surrounding. So that is the observation. That is, the mass falls and the temperature rises. So this is the standard observation, and that Joule observed. Now the point is that, can we think of a reversal of the situation? Can we think of a reverse situation? Can we think of a reverse situation? Means what? That means weight is lifted in the surrounding. That means weight, this implies weight is lifted in the surrounding, and system gets cooled down. So can we think of a reverse situation, that weight is lifted and water in the bath actually gets cooled? It is cooled down. So can we think of, I cannot think of a situation like this. This is I remind you that this is an adiabatic enclosure. Why you cannot do it? Because to lower the temperature of the bath, somebody must take the heat out of the system. Somebody must take the heat out of the system. Otherwise, you cannot cool the system. So, but there is an adiabatic enclosure. You cannot do it. So, of course, you cannot do it. That is the reason. Since by construction, there is an adiabatic closure, one cannot take out any heat from the system. So, there is an adiabatic enclosure. So, heat cannot take out. So, reversal is not possible. So, this is our experience. So, we have constructed a system. So, I can write it in this way, one cannot reverse the Joule's experiment. I can state now. So this is the argument. From this it clearly follows we cannot reverse Joule's experiment. This is our conclusion. This is our humble conclusion that we cannot do it because of the adiabatic inclusion. You will have to break the wall or something, otherwise not possible. So you can rephrase it, slightly rephrase it in a different way, rephrase. That one cannot under adiabatic condition, under adiabatic condition, one cannot lift a weight in the surrounding and cool a system. Again under adiabatic condition that we have in. So you will have to break it or do something to cool it. So you must do something either on the system or surrounding or break it, the wall between it, or something must be done to cool the system. So you can rephrase it again in a different form. Again you can, if I don't use this, so I can write it, one cannot lift a weight in the surrounding and cool a system without doing anything anywhere in the universe. Is it now clear that I have lifted this word adiabatic condition? Under adiabatic condition is a stringent condition. So if you lift it, if you I don't want to use that phrase, then you cannot do anything, that one cannot. Under that condition, it may be possible for us to cool a body, cool a system and lift a weight in the surrounding. But adiabatic condition actually prevents us all throughout. So we must do something somewhere. So without doing something somewhere, we cannot actually do this. So this is a standard statement of the second law that we will find in the books. So if you tell us that one cannot reverse Joule's experiment, it is a second law. I can state second law in this way. So this is basically second law. This actually encapsulates human experience, that we cannot do it. It is our inability to do this thing. It is our inability to reverse the situation. Same thing, it is also the second law is stated in this way. Same second law and the same second law in a more formal form. And in this case, you just make sure that there is no reference to Joule's experiment. These statements are such that we are not making any reference to Joule's experiment. We are slowly drifting away from that experiment, but we have a feeling that from the Joule's experiment that we cannot really do a reversal. Okay, so this is our one of the statements as simple as this. It is our human experience. That is why the second law is basically has something to do with human experience. So this is one of the experiments that we have just discussed now, and just to understand second law. This is the main spirit of the second law, but second law may be stated also in a different way, and we think of some another kind of experiments. Suppose we have already seen the cyclic reversible and cyclic irreversible process under isothermal condition. So, isothermal cyclic process we may consider for expansion and contraction and compression of gases. So, we come to that situation now. So, this is the first experiment that we discussed. So, another kind of experiment. So, isothermal or experiments with under isothermal condition for cyclic process. We consider some experiment under isothermal condition and for cyclic process. So, we have already discussed this kind of experiments in a slightly different context. Let us recall that particular experiment. Suppose I take a gas in a volume V, say the volume is V1, and we have a heat bath, and the gas expands up to the volume V2. So, initially it is volume V1, it goes over to V2, and then I come from V2 to V1 again, and entire thing is kept under a constant temperature heat bath. The constant temperature heat bath. So, if I consider a cyclic process in which I expand the gas from V1 to V2 and followed by V2 to V1. So, if I recall that particular diagram, PV diagram under isothermal condition, temperature constant. So, that was the same curve. I go from volume V1 say to volume V2, and this is my P1 equilibrium pressure P1, and this is my P2 equilibrium pressure P2. So, for going from V1 to V2, I expand the gas under pressure P2, which is a much lower compared to P1. So, So expansion, so work of expansion is related to P2 times, this is my P2. So it goes from V1 to V2. So V2 minus V1 is the work of expansion. And if I come back again from V2 to V1, then I choose my P1. This is the shaded area for this one. And for work of compression, so I choose the pressure P1 and I go from V2 to V1. So V1 minus V2. So W expansion plus W compression equal to W for the cyclic process. So that is equal to P2 into V2 minus V1 plus P1 into V1 minus V2. So W cycle for this irreversible, and you note that this is an irreversible expansion. So this is an irreversible process, irreversible cyclic process under isothermal condition. So it is basically what is the thing that is P2 minus, this is P2 minus P1, this is V2 minus V1, and you can see that this is a negative quantity, this is less than 0. So the work done by the system as we complete the cycle, is negative. Now we know that for a cyclic process, for a cyclic process, W cycle, Q of cycle equal to W the cycle. That is heat. This is a statement of the first law. This is a first law which tells us, that if a system, operates in a cycle and takes heat, that is the Q of cycle, and that is equal to the work done by the system on the surrounding over the cycle. So that is the first law. So that first law is actually captured through the simplest equation for the cyclic process. So you can see that W cycle is less than 0. So the system really does not work. So the work done, you have to work over the system. So you are not gaining anything out of it. So you are not gaining any positive amount of work from the system after complete operation of the cycle. So this is for the cyclic, for the irreversible process. And if we consider the same under reversible condition, so cyclic process, if it is reversible, then we know exactly, we go from V1 to V2 and come back. So this is my P1, P2, this is P1, P2, and what we do here, we for work of expansion, we use PdV. PdV means that each step I change the pressure in going from V1 to V2 for the forward process, and for W compression, that is V2 to V1, so PdV. So, for this process, for the forward process, you have this area, and the same area is repeated just with a minus sign, that is equal to minus of V1 to V2 PdV. So, W of cycle for the reversible process is basically the sum of the two, W expansion plus W compression, and that is equal to 0. So, W cycle for the reversible condition gives you a zero amount of work. So, now for all this process, the system is connected to a single heat reservoir. The system, so I have not talked about the Q. So, Q is the heat which is being transferred in between the system and the surrounding, that between the system and the surrounding, and that heat bath is a single heat bath. So, the single heat bath is actually either transferring to the system, or drawing heat from the system to this bath. So, that is basically under isothermal condition. So, I have a single heat bath under isothermal condition, and for this case, so Q cycle is something that is drawn from a single heat bath. That is the point. Now, you see that if you write the two cases, that is one and these two cases, second, from 1 and 2, we see the W cycle is less than or equal to 0 when the system is connected to a single heat bath. So, when that means whenever you have a system, it is operating in a cycle. If a system connected to a single heat bath and operating over a cycle, that cannot give you any positive amount of work. So, the conclusion is this one. So, I have the first law. First law tells us that W cycle equal to Q of cycle, and the Q of cycle is equal to Q1. That is, I have only heat bath, one heat bath. So, I call the cycle heat is being which flows between the bath and the system is just Q1. So, now W cycle in this case is less than equal to 0 when your Q cycle equal to Q1, that is a single. So, I may rephrase this in a slightly different way, that I can write it as under isothermal condition, I can write that under isothermal condition, a positive amount of work by operating over a cycle. So, under isothermal condition that I have shown that the temperature is always constant. One cannot draw any positive amount of work because it is at best it is 0 when you are using reversibility condition, or it is less than 0, and the positive amount of work by operating over a cycle. Or you may rephrase it again in a way that one cannot operate a system, or write it is impossible. It is possible to get impossible to produce any positive amount of work by a system operating over a cycle and connected to a single heat reservoir. It is impossible to produce any positive amount of work by a system operating over a cycle and connected to a, while connected to a, better use is while connected to a single heat reservoir. So, all that it means that you have a system connected to only a single heat bath, like this one, single heat bath, and you are operating over a cycle, and you cannot draw any positive amount of work from the system itself. So, one heat bath, but you can see that this relation holds good, but there is a qualification on Q, that is Q is something that is composed only of heat from a single heat reservoir. W of a cycle can actually have many heat reservoirs, multiple reservoirs. So, W cycle may be Q1 plus Q2 plus Q3. If you have only Q1, then you cannot have any positive amount of work. So, this is basically the second law, again a statement. And again, this is being, second law is basically an illustration with respect to this experiment. I am making a statement, it is impossible, just stating an impossibility, but you will find that there are instances people have tried to break this law, but they could not really succeed. There are numerous attempts, innumerable attempts to show that yes, I can generate a work from a single heat reservoir at a constant temperature. It is not possible. So, you need at least more than one heat reservoir. That is why so this statement is another statement of the second law. So, second law may be stated in a various way, just as the first law I stated in this form for a cyclic form, and or in the discrete form, discrete version when introduce in internal energy. But this does not make any reference to the internal energy, because we are interested in cycles because of the fact that we want to have some kind of engine which actually gives us work out of heat. So you put the heat into that engine or working medium, and then you get something out of it. So I want the system to come back to its original position, that there is nothing to do with the internal energy at that moment. So this is basically the second law. I will discuss further the second law and what are the consequences in my future lectures. So thank you all for your attention.